how do we leverage Azure Kubernetes services and DAPR with designing and hosting these new architectures on Azure. With that, I'd like to introduce our service offerings. That is, from MICROSERVICES perspective, we are a Microsoft Gold partner and Azure DevOps, Gold application development and integration, and primarily focused on end-to-end services with the app development, app integration, and full end-to-end architecture guidance to all the way to managed services. Specialized in SharePoint, enterprise apps, and mobile apps, and also Power Platform. And we work very closely with Advisix, and I will have Joe Clark explain about Advisix services here.
And hey, good morning, everyone. This is Joe Clark with Advisix. I'm our Director of Cloud Architecture. And Advisix has been a Microsoft partner since basically the instantiation of both companies, which is awesome. And a lot of our wheelhouse for helping folks is with identity, modern workplace, infrastructure projects, M&As, migrations, a lot of work along those lines. And definitely cloud infrastructure help as well, right? So it's kind of a hand-in-glove story here with MICROSERVICES and Advisix working together to get really good outcomes for customers. Okay, and with that, I think I'll take it away. So the first part of what we're talking about today is really sort of the why. Why change an application architecture, and talk about how application architecture has changed. I think that's an important part of looking at the evolution of applications over, really the past 30 years. If we look at the 1980s and pre-1980s, right, largely this was monolithic in nature, where mainframe was effectively the computer, right? This was the only application architecture that existed at the time. And then we did see a move to, client server, right? Right about that, 1980s to the mid 2000s, right? We sort of saw this move to client server, where we saw network protocols get fairly well established. We saw a lot of different things from, the application architecture just sort of evolving, right, into saying the personal computer being a thing instead of a terminal, right? And then in the late 2000s, really to move forward, right, we sort of see this evolution of saying, we have to find better ways of running the software in the same fashion over and over and over again. And cloud really was born out of that need, right, to be able to say we need to be able to build things faster, we need to be able to build things more consistently, and have more attempts at building software faster, and the freedom to fail without large investment. And that really is a large part of where cloud computing really came from. So evolution architectures, this is kind of where we see cloud computing and microservices going really hand in hand. So when we talk about monolith, I sort of mentioned that when we look at mainframe, right? It's really, when you think about how a user interacts with an application, a monolithic application architecture might be something where like you would have multiple instances of the application and services served by a single instance of the infrastructure. So a single server, a single point, a single piece of code to touch, right? Whereas in a microservices architecture, you've actually got basically modular portions of code that you can say, these are services that we run and host and can be called upon to do the thing that they were designed to do. And there is a little bit of difference in this when you examine, how those two can work together. And so if you think about who decided what that architecture really is, maybe a little pop quiz trivia. If you know what movie this is from The Matrix. This is the architect, right? The software architect is the person that's going to be the person that can decide how an application is going to be carved up and what kind of layout is going to be used, how services will be instantiated, what kind of data structures, what kind of access. All that's going to be done by software architects. So if you are building software, you have the luxury of saying, we can understand and decide what kind of architecture we are looking at having, right? If you are running software that was built for you, you have options typically to customize, but not typically a lot of change as far as to what core technologies are leveraged, right? If something is built on, .NET or Python or Java, those are kind of choices that are made early on, and those are very, very difficult, changes that, can be made, but a lot of times it's software architecture, right? What pieces are going to do what? So when we look at maintenance for a monolithic architecture, right, what does it take to really maintain the monolithic mainframe mentality mindset behind an application? Typically, it's a big event, whenever you go to update that, right? If you think about, updating many servers and having a patch weekend, right? There's lots of people involved. It's a highly visible event. There's a lot going on. Updates typically don't occur often, quarterly, maybe twice a year, right? Where you're seeing there's updates that happen then. More often than not, you need a maintenance window. Like, hey, there's going to be an outage. There's going to be a downtime. There's going to be a period of time where we are not able to access the application, and we need to be okay with that. And typically, every part of the application is touched during an update. It's like, all right, we're moving from .4 to .5, and look out, every feature we wrote in that major release is coming at you, whether you like it or not, and let's hope everything works and we don't have to roll back, right? Monolithic maintenance is kind of like getting your car worked on. It's like, we got to take it in for work. We got to get it on the skids. We got to get it out of, operation for a little bit of time to have it worked on in sort of a traditional fashion. So when we're talking about monolithic maintenance, this is effectively a large part of what this ends up looking like. And when we're maintaining a microservices architecture, it changes some of how we actually update components in the software that we're responsible for running. First and foremost, it really should not be a big event. We should be very comfortable with pushing small changes frequently in a microservices architecture, which gives developers freedom to build faster and build with more confidence that they can quickly roll back a small change. There's fewer teams involved. You don't need a massive team because there's typically distributed responsibility along with those distributed services. So smaller teams are required to be called upon for updates. Updates occur very often, right? Update, all the time, and push changes frequently. And then, sometimes there's a giant push to production lever, right? That sometimes people will say, hey, once a week, once a month, whatever. Like we would decide we're going to push, merge our branches together and push, code into production, and say, hey, we might have a gate or a lever that we would like to make a business decision on when to push to production, which is really good. Typically, one of the services is touched during an application update when we push things to production. So it's, it can be multiples, right? It can be multiple things together. But typically we're going to say, hey, if we update one thing at a time, that allows us to basically update and deliver value faster than, a quarterly or twice annually perspective. So maintaining a microservices architecture might look more like this than actually getting your car serviced, right? It is maintaining the car and running it while it's running down the road, right? So I'll let that loop through one more time because it's just too awesome, right? I mean, maintaining a microservices architecture is working on the car while it's running down the road, while you're gaining momentum, while you have users in the system and leveraging it, right? So really when you're looking at what this allows you to do is, this is obviously a terrible idea, and I do not recommend that you sit on a car while you're doing this, so maybe a bad example. But the idea as far as car maintenance is concerned is it's the same philosophy. People want to be able to use their car while they're building new features for it and have those features as fast as possible. And we really see that, maintaining and pushing new features into software, that's a giant part of being able to do that very quickly and on the fly. So does, moving to a modern application architecture solve all my worries? Not necessarily, right? There's giant code bases that exist today, and that can be a big project to move that, right? It's an architectural choice where you want to say, I want to have good deployability and good testability. I want to be able to make that choice myself. There's operational changes that come with moving to that. I mentioned, it's smaller teams, right? There's organizational responsibilities where if you're going to change an application architecture to microservices, you might get ready to say, hey, we need to change how we're structured from our people process and make that work. And you've got to own the application architecture. Again, like I said, if you're running someone else's built software, this is where you don't have that option to say, I'm going to dictate, the specific technology choices that you've made during the building of that particular application. Okay. So this is where it sort of leads to a culture clash, right? Where we have developers who love change, love new things, want to build, want to, have the latest things to be able to try to build with and build value for customers. And then you have infrastructure engineers who basically are saying, yeah, we like things that are dependable. We like things that have high uptime. We like things that necessarily don't move often, right? And so the little quip that I sometimes use is that developers want to play with the new toys, but never want to have to change the batteries, right? And that leads to infrastructure engineers basically saying like, hey, we've got we've got to make sure that if we're running infrastructure here, that it's kept up to date, that it's secure. There's a lot of things that we're concerned with that we maybe want to be more slow moving on. So there's a culture clash there, right? So I won't read through all of these, but there's definitely a lot of differences between a developer and someone that is responsible, for infrastructure on the back end, and saying that we're responsible for ensuring services continue to run, that we have stable platforms. And the one that I'll call out with, right, is basically, it's kind of summarized in the fifth, line item down here, which is comfortable taking risks, right? Developers are comfortable saying, this is a new tech, this is new, we're going to build it, we're going to run it, it's great. And infrastructure engineers are typically more risk averse, right? Like if it's a risky operation, we're not necessarily going to be gravitating towards that, right? Because it's different philosophies, right? It's almost like developers and operations are two different units, and combining them together really does start to say, like, hey, that really is what DevOps ends up boiling down to, is saying we want to build, we want to test, we want to release, deploy, operate, monitor, plan, and then have that feedback loop just be much, much tighter than a release a couple times a year. So really what does DevOps boil down to is it's increasing the value to customers, and it's respect for people, right? So when someone says, are you guys doing DevOps? This is what it boils down to, right? So the technologies are part of it, but it's really saying we want to increase value to customers faster. And what that means is, yes, oftentimes we need to do all the things we talked about: faster feature releases, better stability, more testing, all those good things. That's how we can increase value to the customers, by being able to be more frequent. And when we talk about cloud and how that comes about, this can be really, really difficult, because we're saying, okay, say for example we want to run this in a couple different environments and in a couple different clouds. It can be like saying, do we have anybody that knows all the cloud providers? Do we have anybody that knows AWS, Azure, Google, and like the number of services that exist in all of these different platforms is staggering, right? And there are just a bunch of different services that you can leverage in each of these cloud platforms, and some of them are similar and some of them are different in very nuanced ways. So to try to develop a code base against multiples of these and have that work well is certainly challenging, right? So how can I realistically deploy apps in multiple clouds, right, and build with speed? It's almost like we need something to abstract the application in a way that's native to cloud providers. Almost like it needs to be something portable, like maybe containers, maybe something that could contain that application, right? And so when we talk about containers, and that's really sort of the first thought here behind, building with container orchestration, is understanding what the container is. And this isn't a new problem. This is actually an old problem that's been solved through history a couple times before. If we look at cargo transport pre-1960, there was many different types of goods, and there were many different concerns, right? Like, I really don't want my coffee beans next to gasoline, and I'm concerned with what sort of things I might have. And from a transport perspective, they have a different concern, right? Their concern is that, hey, like, I want goods to be moved, right, to with different services. I've got a bunch of different types of things, right? So as they're looking at that, it's understanding that the matrix for support is very difficult. If I have a different thing to transport a car on a train versus a car on a boat versus a piano and a truck, it's very difficult to basically build a matrix for stability to say we need a solid handoff, right? So the solution there was the intermodal shipping container right around the 60s and 50s, right, where there was a couple different types of them, but this one that's basically the size of a semi really sort of took over as the standard, and makes up, to my understanding, about 70% of all the containers that exist today in the world. But the benefit here, right, is it standardizes and seals that until it reaches the final delivery, right, for the goods. And the benefit for the transport is that it's effectively loaded, stacked, transported efficiently across many different modes of transport. So they can bank on, hey, I know my hooks are here. I know I can drop it on this, this truck bed. I know that I can bank on this because it's a stability, right? And as we look at applications, it's actually very similar, right? A static website, a web front-end service, an app service, an index, right? Message queues, middleware. those are all different across many different environments, right? Like a laptop versus a cluster that you run on-prem versus a cloud provider A, cloud provider B. The same problem, right, can end up being solved by the leveraging of containers, right? And saying we want to make that application portable so that we can run it in many different environments consistently on pretty much any hardware or cloud platform. So that's where we're saying, like, hey, if we can, solve that problem in the same fashion, where we are building software artifacts that are running in the exact same fashion across multiple different types of infrastructure, that gives us sort of that nice warm blanket of stability and comfort in saying, look, we know our artifacts are the same. So there might be some environmental changes, but we know for sure that the software we're building has certain inputs and certain services that need to be exposed, and we can be confident in that as we're moving forward and building. So containers are, basically a common tool that's used to build modern application architectures because of all these things that are listed here. They're portable, they're testable, they're deployable, and they're consistent. And those are a lot of the things that we end up seeing folks say, this is really what we want to have when we are looking to build software, right? The UI, the services, and this is not necessarily an easy battle or something that's that happens very, very quickly. But the why is extremely important behind this. Why are more enterprises embracing modern application architectures? Because like we said, it's just an architecture choice, right? You can do things in a monolithic fashion. You can do them broken out. You can make many different architecture choices. But why are many enterprises embracing this? Faster throughput. The developers can build faster when they're given the freedom to fail and the freedom to say, I want to have more iterative builds of my code. That's going to allow me for more time to do integration and unit testing, right? So to increase developer productivity, this is absolutely a way, right? So if, for example, you build software and every time you want to test it, there's a 3 to 4 hour process of standing up a bunch of VMs and load balancers and everything else and middleware and and caching, and you got to set all that up, and that takes like a couple hours to set up. That process of like building that is incredibly painful when it comes to developer productivity, right? So making sure that features can be built by removing every barrier to building successfully is a key attribute. Again, increasing value to the customers. It's a key tenet of DevOps. And when we talk about DevOps and saying increasing the value to the customers, that basically means building more useful features, getting more user stories solved and moved across the board, and bringing more value to those customers, right? And saying like, hey, what if we could bring this feature to market and that would just be amazing for our customers? And if that takes, a sprint planning that moves out, 2 to 3 years because of reasons, then, you're going to be slow moving as far as to the value you can bring. So how fast you can have on your time to market, very, very important as far as embracing modern application architectures. Operational efficiencies, right? I mean, so I think it's a fair thing to talk about when virtualization has pretty much become table stakes now in most organizations, right? So there's some sort of shared storage, there's some sort of virtual machines that are running in most locations, whether that's on-prem or whether that's in a cloud, right? And why is that? It's table stakes because of operational efficiencies. It's just much easier to have, a couple virtualization hosts that have maybe 50 to 80 VMs in them than to have racks and racks of servers 1-to-1 in a ratio with a bunch of different network drops and everything like that. It's just crazy to think about how that was how it used to be, right? If we go back to the, the Fresh Prince of Bel-Air slide, right? Like in the 90s, like, hey, you had a server that ran that, right? In one of the first jobs that I had, I was responsible for an SMS server back in the day. And I knew that server and I loved it and I hugged it. But, it evolved a way to say the value wasn't in necessarily having a physical server, it was providing that service. So virtualization sort of closed that gap. When we're talking about operational efficiency in building software, it's extremely important to note that the more features we have, that's going to be great. But when we're running software, containers, are basically the next evolution of speed and deployability and testability that, basically we said when we went from physical servers into virtualized servers, containers and container orchestration are effectively that next layer, right? And I affectionately usually say, right, when we went from physical to virtual, we went from, days to hours, right, to get things working. Containers are from hours to minutes, right? Because it is just so much faster to instantiate software on already running dependable platforms that can just instantiate and orchestrate containers. So it's effectively just saying, like, hey, that operational efficiency, that's where we're saying we're being more effective with our time. We're not waiting for processes to complete. We're thinking about how we can deliver that value. And finally, accelerate time to market, right? Just understanding that if we have good ideas that are going to help our companies or, in turn, external customers of our companies, getting those ideas to market faster is going to be beneficial to the company, right? A good idea is something that should definitely be ran with 100%, accelerating time to market, almost nothing, no need to go further on that, right? That's pretty well understood. The faster you can get that idea in the hands of customers, satisfying the needs, that's going to go hand in hand with increasing value. So with that, we've talked a lot about why modern application architectures are really important. And at this point, I'm going to hand it over to Ravi, who's going to actually talk through some of the how, right? So we talked about why this is important. We talked about feature development, speed, and all this good stuff. Let's now talk about maybe some of the how and how we've actually done some of this together, leveraging some really interesting architectures. So Ravi, I'll stop share, and I will hand it over to you to go ahead and take over share. And we are seeing your screen, my friend, so we are good to go.
Awesome. Thank you. That was my question. You read my brain. Okay. Thanks, you. I think that was great on how you articulated on why we need containers. So let's learn now about how, the question how, right, as you were saying, how Azure Kubernetes, once we have the containers in place, how do we orchestrate them? How do we make decisions, or how do we design the microservices architecture when you have a monolithic app, right? So let's concentrate on that piece now a little bit. So here, what you're seeing here on the screen is that it's a TAILWIND traders. Is a fictional use case that I just wanted to use to show you how the transformation could look like when you transform from your monolithic architecture to microservice architecture, right? So TAILWIND traders is a traditional e-commerce shop. On the left side, you can see the monolithic architecture here with all the modules, be it products, cards, stock, everything is bundled into the same project, the monolithic project. And it could become something like this, right? On the right-hand side, what you're seeing here, the microservices architecture. In this use case, basically, you can see here all the modules that we have in a single project here are divided into multiple services, right? Be it multiple services, and those services can talk to each other, and we have API gateways fronting these services for the clients, which will provide a communication platform for the client and stuff like that. So why do we need to do this, right? I mean, as Joe was mentioning, it allows development teams to progress faster and allows them to use latest technologies without any kind of dependencies on the other team or other modules there, right? So in this use case, for example, TAILWIND traders wanted to implement a feature called Smart Shopping that should allow users to upload a picture and let them search the inventory. This kind of feature basically needs some kind of artificial intelligence or machine learning kind of technologies, right? Because if we want to provide a feature that allows these users to upload a picture, we should be able to analyze the picture and find the objects in the picture and show them the relevant results, right? So this kind of feature needs some kind of AI in it. So if you look at the monolithic architecture, it was .NET, and most of the libraries that we use for AI or ML or in Python. Even in .NET we can do that, but it'll be easier in Python. So in a traditional sense of monolithic, that could be a showstopper, right? Because of this technology limitation that you can only use .NET there. But when it comes to the microservices, they can always spin up a new service with the technology choice, whatever they need, and add a new service and get to the market faster with that kind of feature. Not just that, right? Microservices architecture provides the ability to scale components individually, not just in a monolithic architecture. If you want to scale, if you want to scale, you need to scale all the modules together, right? But in microservices architecture, the modules are very light because you are decomposing your monolithic into multiple services, and they can scale components individually. And this is where Azure Kubernetes service, Kubernetes or Azure Kubernetes service can really help us basically to provide that kind of reliability and scaling. What I mean by that is, for example, let me just jump into your screen here, right? Let me. So what you're seeing here is the same application that I've showed you right earlier is deployed on our Azure Kubernetes service here as multiple services. Sorry, each and every service that you're seeing here, if I go to services here, for example, if I go to here, you can see here each and every service, be it products, coupons, profile, is deployed as a individual service in here, right? They have their own IP addresses, and each and every service is deployed as an individual service. So let's just say, for example, this TT web is nothing but the skin of the website that I was talking about earlier. For example, let me show you the website too. So this is the website, right? So the skin, whatever we are seeing here on the screen, is responsible. It's a React project, and this is the service that is hosting that skin, right? So if in case if we wanna scale this particular component quickly, right? Here, how can we do that? So for example, let me just do this, right? I can do something like this. I'm setting a deployment. I'm setting the deployment to raise. Oh, sorry, not this one. I'm just defining a rule for this particular website microservice to scale from 1 to 3 whenever there is a CPU percentage is greater than 25%. Right? That is the kind of rule that I'm defining here. So I can just define the rule here. Okay. Okay, just give me 1 minute. Here, settings. Yep, sorry about that. I just need to log in here quickly, and that I select the right subscription there. Yes. Okay, while I do this, maybe I can move on here and explain you what I was trying to do here. So what I was trying to do here is I wanted to basically define a rule on this particular service that tells whenever there is a load that is increased, whenever there is an increased load there that increases their CPU percentage by 25%, it is going to scale automatically. Right now, what we have in here is we have only one pod that is running here, and that if I go into this pod, there is only one container that is running. So whenever it reaches certain CPU percentage, basically it needs to replicate automatically, and it needs to create multiple containers here to accommodate the load, right? So that's what I was trying to show here, because I still need to log in. Considering the time here, I might move on for now, but I will come back to this if we have time at the end. Sorry about that. So of course, along with all these benefits and good things, I mean, there'll be some challenges that we can expect as part of the modernization journey, right? Reliability and, for example, reliability and message guarantee. When implementing strategy for service to service invocation, or we need to think about reliability, right? So what happens if a failure occurs? How are we going to retry? Failure could lead to data inconsistencies when you are dealing with microservices. When designing microservices, portability is also something that we need to keep in mind. Containerization could provide portability to move applications irrespective of the infrastructure, but there will be technologies that we use that are tightly coupled, right? That mandates us to change the code whenever we need to swap those services. So in order to address those kind of challenges, we need to make sure that we think through some of these design patterns, right? And the building blocks as part of the design phase itself. So here are, I mean, some of them that can help us build a robust microservices architecture. For example, communication between the services, the first thing, right? Service to service invocation. This is very important. So when we are getting into microservices architecture, there will be needs that our services should be able to talk with each other, right? So there are multiple ways services can talk with each other. It could directly invoke a service, or they can communicate using a queue mechanism, right? Like publish and subscribe, where one service can put a message in a queue, and the other service who is subscribed to that particular queue can get notified. So that's like two ways of communication happens between these microservices, right? So while thinking about communication, we should also plan to make sure the communication is secure. We need to think about the reliability, like what happens in case of the failure, right? How do the program retry to communicate with them again in case of failures, or how do we define access policies that regulates services communication, right? For example, let's just say that we have two microservices. One of it is doing maybe something like a checkout microservice, and the other one is something like a processing order microservice. So once the checkout is finished, we need to process the order, right? So we'll end up having two options there: make a call to checkout, get the order ID, and make another call to process order, right? When you have two different microservices doing two different things. But we can have a single checkout service itself communicate with the order processing service to finish that in a single transaction. That is one more way of handling it. So that is the reason having that communication between these services is very useful and important. And sometimes the communication could be from an external resource, right? Our application might need to do something because of an event that happened by an external system, or it could be a notification from a different application, or sometimes we need to notify an external system based on an event that happens inside our application. So that is where bindings will help us. This is can help instead of polling an external service, or polling an external service to get the updates. Using bindings, we will get notified basically whenever an event happens, which is external to the system, right? And one more key important thing is observability, right? Robust monitoring is a must when it comes to microservices architecture, right? When an application whenever you're building an application, right, understanding how the system is behaving is an important part of operating it. I mean, that includes having the ability to observe the internal calls of an application or measuring its performance. So we are aware of the problems as soon as they occur. Instead of users reporting it even before, we should be able to identify the problems and mitigate them, right? So that's the goal. So this is a challenging thing for any system, but it is even more challenging when it comes to distributed systems that has multiple microservices. So that is something that we need to look into and think about it more when we are designing for microservices, right? So, or when it comes to storing secrets and configuration outside of the system storing secrets and configuration outside of the system is one of the key DevOps practice, right? We should be able to protect the secrets and access them securely from the apps. At the same time, configuration needed by the system is changing, basically it's ever changing, and application should be aware of the configuration changes that are happening to the config, even when it is resides out of the system. So these are some of the building blocks / design patterns that we need to think about when getting into microservices architecture. But that is where DAPR, right, distribution application runtime, comes into picture. It's an open source technology started by Microsoft to support all the patterns that we discussed earlier, right? And applications and these applications are more portable irrespective of where we run our applications. So we could develop our services in any language. At the top, you can see here, we should be able to our microservices could be in any language, right? It could be a Node microservice or a Python microservice, .NET microservice, it doesn't matter. DAPR provides us a way to implement these design patterns easily. It makes the application more portable, irrespective of where you are hosted or what technology you are using to implement these kind of things, right? For example, you could be hosting your Kubernetes cluster or anywhere, right? It could be on Azure, AWS, or GCP, right? If you take state management, whenever you are hosting this microservice anywhere, if you take state management, for example, your application, for example, could be using a store like maybe a Redis store or a Azure Cosmos DB to maintain its state, right? There'll be different scenarios where you might be using a Redis server locally, maybe during as part of development, and use maybe the Cosmos DB once you deploy into Azure, right? So DAPR can help you encapsulate that implementation and make your application technology agnostic, right? So that means irrespective of whatever the service that you are using here, be it any service, your microservice will be talking through DAPR API, and DAPR will understand exactly how to talk with different kinds of stores or different kinds of message queues and stuff like that. So your application code doesn't need to be changed when if you want to talk to a different store or a different queue system. So same thing when we implement something like this with the typical publish subscribe pattern, right? So common patterns for service to service communication here, basically where, as I was explaining earlier, where one service posts something and the other service who is subscribed to the queue can get notified with the message, right? As you see in the picture here, depending on where we hosted, our microservices architecture could be using different kinds of services, right? It could be Redis Stream or Azure Service Bus or GCP publish subscribe service to achieve the same thing. But DAPR helps you to stay technology agnostic and easily integrate with any kind of service as needed. So in order to demonstrate this, I just wanted to talk about a simple application first to show you how exactly this happens. I have a simple Node application that uses different stores to store and retrieve the state information, right? So how does DAPR is able to do that, right? So basically DAPR runs in a fashion like a sidecar architecture. That means, that means an instance of DAPR runs along with your app, as a middleware between your services like state stores or your secret stores or state stores, anything like that. It acts as a middleware between those services and your application. And your application don't need to directly talk to these things. It uses the DAPR API to invoke and use some of these state stores, right? That's why, and let me show you here an example application that I have in place here. So I have a simple Node.js app here. It's an Express app. It just has two endpoints. If you see here, a get endpoint and a post endpoint. The post endpoint is nothing but new order. That means whenever there is an order, it needs to take an order and store in the state store. And a get endpoint whenever you need a specific order. It should be able to talk to the state and basically get the order information, right? As you see here, what I'm doing here is I'm building a state URL here because, as I was mentioning earlier, whenever you deploy an application like this using DAPR, DAPR is in Sidecar architecture, right? So your application will communicate with the DAPR rather than communicating directly with your state store. That means so this is the URL that I'm building. So your application knows where how to communicate with the DAPR, right? So in here, I'm just building this as a state URL here. And in the get call or the post call, all I'm using is that state URL. I don't have any service specific code here. I'm not talking to Redis directly, or I'm not talking to Azure Table Storage directly and stuff like that. So so the way how it works is, let me start this app once. So if you see here, what I'm doing here is I'm using DAPR to get my application up and running. I'm just assigning this application with a app ID called Node app, and I'm specifying this app should be running in port 3000. And at the same time, I'm specifying the DAPR HTTP port, which is the API, the DAPR Sidecar instance that is going to run, right? That I was showing you in the picture here. This DAPR Sidecar will be running under a 3500 port, and this is the port that it will take. And when I'm building this URL, this is how it communicates with the DAPR, right? So I'm specifying two different ports here, and I'm specifying one more thing called components path, which I'll be talking about in a minute here. And I'm just doing node app.js to basically run this app, right? So let's just see. Run this app here. So you can see here, my application is up and running now, and my Node app is listening on the port 3000 here. So now what I can do here is I can invoke the API. See, all I'm doing here is since my application is up and running there on 3000 port, I'm just invoking the same app ID. This is the app ID that I specified earlier when I wanted to run my application using DAP, right? So I'm just invoking the same application, and I'm specifying the method which I want to call, and I'm specifying a data file here, sample.json, which I have in here. It doesn't have much other than an order ID, so I'm expecting. Whenever I call this endpoint, it just take the sample data and store it in the state store, right? So maybe I'll just put it as 56 or something. So when I do this, sample.json app invoked successfully, right? How did now let me go to my Redis store here, and let me just refresh. You can see here my order is updated here to 56. That means it basically my application was able to receive the request and store that information that I'm sending in a Redis store, right? And how was it able to do that, right? So as I was mentioning here, it was talking to the DAPR port, which was running on DAPR instance, which was running on 3500. And basically what happened is there is a component that I defined here called state store, which defines this Redis object, right? The Redis server is running on port 6379 here, and I have a password mentioned here. It doesn't have any password basically locally. So my application was able to talk to DAPR, and DAPR was able to talk to this component and make that change, right? So what happens if I need to change the store easily, right? For example, I can say something like this, the table, right? I have different component here defined called state store table. This is nothing but it is also a component, and the type of the state is different here, right? If you see here, the old one, the state it's a Redis store, and then the state store table is a Azure table storage. This is just a metadata that I'm supplying, basically, so my application can talk to the Azure table storage instead of a Redis storage here, right? So let me just go ahead and maybe stop this. Install. Yeah. So now I can go simulate the same kind of, maybe I'll change the number to maybe 59 now, right? Now I can simulate the same. I'm invoking my app again using the same method called new order, and I'm giving a new order number here, right? So now if I do here, this one, app invoked successfully. So what happens is if I go to Redis now, here you can see this is not updated because now my application is using the Azure table storage, right? So if I go to the Azure table storage here, for example, I can just refresh here. You can see here the 59 order that I gave. Now my application is using the Azure table storage as its state store, right? So all I did was I don't have to change any kind of application code. I know, I mean, technically I changed this particular piece of line here, but eventually, but ideally, what happens is now just to demonstrate, I have like two different components defined here. Basically, what happens in real world is you can have only a single component. Once it is deployed to the cloud, basically you will swap this type from Redis to any different storage that you want to use. And provide the metadata accordingly, and your application will start on using any kind of a different state store or any kind of a different queue mechanism and stuff like that. So what I was able to demonstrate here is when you have a application, irrespective of the programming language that you're working with, it becomes technology agnostic by using DAPR, right? So that's the key advantage of using DAPR here. So basically, these are the two things, right, that I changed. Basically, in order for my application to be using switching between two different stores, all I had to do was in the definition, I need to change from state.redis to state.azure.table storage and provide the metadata accordingly here. So my application was able to basically find out the new storage without having to, in real world, in generally, if we don't have DAPR, for example, right? What could happen in the application itself? We'll have a lot of code that is tightly coupled, that is integrated with either Redis SDK or Azure SDK. To communicate with this kind of state store. So not just the state store, right? That is just one example that I was showing you. It could be when it comes to publish or subscribe components, it could be a Redis It could be either Redis, or it could be Azure Service Bus, or it could be GCP publish subscribe, right? So basically, in order to define any of these design patterns, basically it will provide you, DAPR will provide you different features like uh, making your application technology agnostic, whether whatever the service that you are using. For example, if you take secrets, right? Some people use Azure Key Vault, some people use HashiCorp Key Vault, right? So those kind of things, if you want to switch between those things for some reason, DAPR will provide you that encapsulation layer and access and middle layer uh, between your microservices here. So, I mean, locally, we can easily install DAPR locally and run this as you have seen using the DAPR CLI commands. We can get it up and running. But when it comes to Azure Kubernetes service, right, there is an extension available to install DAPR on your K8s cluster. And once that is installed, basically how it looks like is once you install the extension, it will be something like this, right? It will spin up different system services on the cluster, which are responsible for different things. For example, what we have here is Azure Runtime Injector, right? So DAPR Runtime Injector. DAPR Runtime Injector is responsible to inject the DAPR container whenever you spin a new instance of your app. Certificate authority, again, one more thing is the certificate authority can manage and manage the secure traffic between your services. So whenever you spin up a service in a pod, DAPR will be spinned up automatically as one more container in the same pod. Any communication which your pod will go through the DAPR API. So that way you're getting that technology, being that technology elastic. And the DAPR takes that heavy lifting of communicating with any service we picked and encapsulate the implementation, right? For example, as I was mentioning earlier, it could be anything. The example I showed you was a state store, but it could be anything. For example, it could, as I was mentioning, it the Azure Key Vault to store your secret, or a HashiCorp Key Vault to store your secret. Your application doesn't need to know what the implementation. DAPR will take care of that integration and provides you that portability. So when it comes to this extension, right? Once this extension is installed, basically how it looks like is I can show you a quick thing here. As soon as the extension is installed, you can see something, a new namespace will be created called DAPR system. These are the 4 services that I was showing in the presentation, right? DAPR Sidecar Injector, DAPR Sentry Operator, all these system services will be installed and up and running automatically. And whenever you deploy a new application in here, right, on the new application in here, basically what happens is, let me just show you. Not that. So I have one of my applications deployed here. These are all the different microservices that are responsible for that functioning of that application, right? So maybe let me just go into the viewer service, right? So in the viewer, if I go to parts, you can see here there are two in my pod. There are 2 containers running. One is a viewer, which is nothing but a Python app that I have in here. And there is one more container that is running as part of the pod, which is nothing but the DAPR, right? So whenever we install DAPR on AKS, basically what happens is when you deploy this new application, that injector service that I was showing you earlier, will automatically spins up and deploys that sidecar into your pod, right? So that will be responsible for any kind of communication from inside your pod to any of the services that we are talking about here. I know this is a very high level and a simple application that I have shown you here. But in case of any questions, please let me know. And there is a lot to learn about. This is, think of this like a 101 for DAPR, right? So when it comes to the DevOps workflow, right, this a typical DevOps workflow could look like this. The one that I'm showing you here is from Azure DevOps. And whenever a developer check-ins, I mean, this continuous integration and continuous delivery, the same thing would happen here. A pull request would happen, and once the pull request is done, reviewed, merged into your master, a pipeline can take that and make the deployment to Azure Kubernetes service. But as long as your DAPR is turned on that service, once your application is deployed, basically what happens is that sidecar of the DAPR instance will automatically be spinned up and showed as part of your application deployment there. So any questions so far? I know we have only 3 to 4 minutes here, so I want to just leave the room for any questions. I'm not able to see the chat, so I'm not sure.
It doesn't look like there are any questions, Ravi.
Yeah, sorry, I'm not seeing any either here.
Okay, so as I mentioned earlier, I mean, this is just a basic introduction to DAPR, but if you have any other questions on how to implement a DevOps strategy for your microservices when using DAPR, or how to implement some of these design patterns, please feel free to email me or Christopher in the call here, so we can get back to you and discuss more about it.
All right, thanks so much, Ravi and Joe. Really appreciate it. All the information that we received here today, that was great. This meeting was recorded, so we will be sending out that to all the attendees and all the people that were unable to make it. I think that's pretty much it. Really appreciate your time here.
Thanks, everyone. Yep. Thank you.
Thanks for the time, everybody.
Yeah, thank you.